In this video, we are going to go over section 9.2, separation of variables. The goal of this section is to solve differential equation through a technique known as a separation of variables. So what's different about last chapter or previous concept versus 9.2 is we are now going to have an equation where the derivative function is also part of our equation. So take a look at kind of like the first problem or second problem. You can see that you are given this differential equation and you have two different variables, x and y. Sometimes you might have just one, but sometimes you might have more than one variable. So if you have both x and y, our goal is to separate the variables. So we are going to put all the y term on the left-hand side and then all the x term on the right-hand side. And then we are going to use antiderivative to get rid of the y prime so we can solve for y function. So the solution for our equation is y function, not a value, an equation. Okay. Later on the chapter at the end, we are going to go over three different application problem: exponential growth model, limited growth model, and logistic growth model. They all have a very similar thing, two things being multiplied, the growth or the decay factor k's, and then you have another product with certain limits growing or logistic growth. So take a look at exponential growth. The keyword that you're looking for is the quantity. Y is proportion to the amount of present. So it's literally just a very simple one. Y is proportion to amount of present. So K times Y. Here, the limited growth, you have the difference. So you should have somewhere in the sentence of your problem the difference. So quantity of y is proportional to the difference between y and the limiting value m. So here's the difference between the y and limiting value m. And then you have y is proportional to, so take the only difference between exponential and then limited growth is this part here, proportional to the amount present. So there's your y times the k, and here you have a y times the difference between y and m. Okay. Now logistic growth is proportional to both amount present and the difference between the y and limited factor. Now the proportion to both amount present, that's this part here. So that's why you see the km. And then you see the difference between y and the limited value m. That's this part here. So in a sense, it's a little bit of a combination of exponential and limited growth. So when you are going through and reading the question, look for the key word. Is it the difference between y and a limited value, or is it both amount present and the difference between y and m? So you can distinguish the difference between the three. Now these equation, notice that it's given as a differential equation. So eventually you need to apply the same thing, separation of variable with y's and t, and then solve for the y. These are kind of challenging one to integrate. So on the next page, I give a model and then solution function. So you do not need to integrate all the time. Some of them you still do when you don't have exact same condition, but most of them, the solution function is all written there so that you don't have to integrate it each time. We can just use this equation and get the y function right away. And these are some graphical representation of our growth function. Here we also added the decay. It's almost same thing. If growth is a positive, decay will be negative. And then these are some uses, so you can read through and see when we use these functions. Okay, so some of the example, for example, epidemics, rumor spread, all these, some of the homework has it. So if you're looking for these keywords, you can also match which growth it is. So we'll go through a total of 6 examples today and then end the section 9.2. Let's begin with something very easy and very straightforward. So problem 1 and 2, find the general solution for each differential equation, then find the particular solution satisfying the initial condition. So we are looking for two things, general solution and then particular solution satisfying these initial condition given. General solution will be y equal to some function, and then you are going to have just a c attached. Particular solution will have same function, but we are solving everything, even c as well. So we are actually finding the constant. Okay, so here's how we do it. We first one, you can rewrite the y prime as dy dx, and then you have e to the x over e to the y. Now you have two different variable, x and y, so this is where separation of variable occurs. We need to put all the y term on one side and then all the x term on the other side. So here, these are my y terms, dy and then e to the y, and then x is right over here. And then you can use, this is a proportion, so you can use cross product. So I have e to the y dy is equal to e to the x dx. Once you have all the one variable on side and other variable other side, we are going to integrate it so that we get rid of the dy's and dx. So we are just having a solution y equals something. So let's integrate it each side. This is an easy one. That will be e to the y plus c sub 1. Now I'm going to put c subscript 1 because also we have another constant from the right hand side. Okay, and then this is a little trick. Imagine this. You have a constant and you have a constant. So think about this. I'm just going to put it on the side. Let's say I'm just giving a number. I have constant 2 and then I have constant 5. Then you can actually combine into one constant and then plus 3. So this is where I'm going to do the same thing too. I'm going to combine these two and then put it on one side as just one single constant. So I have e to the y is equal to e to the x, and then I'll just use capital C with the no subscript. So I didn't like cancel out C1, C2. I just combine it into one big constant. Okay. All right. So we need to solve for y because we need to find the solution, general solution. So we need to keep going. So let me put this on over here. Now here at this point, to get rid of it, I'm going to have ln applied, right? So let's apply the ln. So I'm going to have ln of e to the y and then ln of e to the x plus c. Then I'm going to have y is equal to ln of e to the x plus ln of e to the x plus c. So this will be our general solution. So this part over here is the general solution. Okay. I solved for y and I left it as a general c term. Now we are actually going to find out the particular solution. That's the second part. So I'm going to be using this condition, initial condition given plug it in to solve for c, and then at the end write down nicely into a y function without leaving as plus c. So let's do that. So this means x value, this is a y value input and output. So that means I have y as a ln 5 is equal to ln e to the 0 plus c. Anything to the 0 power is 1. So I have ln of 5 is equal to ln of 1 plus c. Okay, now to have the c solved by to solve c, I need to apply e function. Okay, do not distribute ln. Ln is not a number, it's a function. So e raise it to ln 5, e raise it to ln 1 plus c. These cancel out. I have 5 is equal to e. This cancel out 1 plus c. Subtract 1. I get c is equal to 4. So I know what c is. So from the general equation, I'm going to substitute. So y is equal to ln e to the x plus 4. Now this is our particular solution, satisfy our initial condition. All the way up to now, we always left it as plus c whenever we differentiate because we don't know what the constant term is. Now you can solve for c because you're given this extra information. So these two are my solution. Okay? All right, so that's the general strategy. That's how we solve for that's how we are going to solve for our equation. So let's do another warm-up problem, number 2. Okay, and then move on to the 3 application problem. Number 2, again, the y prime is also dy dx. So write it out this way, 1 over y cubed. So let's separate the variable. So I have y cubed dy is equal to 1 dx. I have all the y term and then other one on the other side. Let's apply integral to get rid of dy and dx. So I'm going to have raised power divided by new power. So that's going to be 1/4 y to the 4th plus c of 1. The antiderivative of 1 is just x plus c2. Same strategy, I'm going to combine this one into one big c, one big constant, so x plus c. We need to solve for y, so I'm going to multiply the entire equation by 4. So I'm going to have y to the 4th equals 4 times x plus c. Okay, and then I'm going to 4th root it to get rid of my 4th power. So y is equal to 4th root of 4x plus c. Again, this will be my general solution. We solve for y and we leave c as a general term. Okay. Now let's go ahead and then use our initial condition to solve for c to find a particular solution. So I'm going to plug it in. So my x is 1, y is 4, so that will be 4 equal to 4th root of 4 times 1 plus c. So that's going to be 4th root of 4 plus 4c. 4th root, to get rid of it, I'm going to raise by 4th power. So 4 to the 4th power is 256. On the other hand, the roots cancel out. 4 plus 4c. Subtract 4. So I have 256 subtract 4, which is 252. divided by 4. So C is equal to, I get 63. So my particular solution will be y is equal to, replace the c here, 4th root of 4 times x plus 63. That will be my particular solution. Okay. All right, so we got a little bit of warmed up. Now let's go on to a application problem. So you are not given any equation. Okay, you're just given a information, and then we need to find out if these one are either exponential growth, limited growth, or logistic growth. Okay. So let's read it through. In a study of ciliate protozoans, it has been shown that a rate of growth of the number of Paramecium quadratum in a medium with a fixed volume is proportional to the product of a number present and the difference between an upper limit of 375 and the number present. Here's the key word to distinguish between the three. What does it say here? We have a fixed volume. Something is proportional to the product of the number present and the difference between the upper limit and the number present. Suppose medium initially contained 20 paramecia. After 1 hour, there's 150 paramecia. How many paramecia are present after 2 hours? So here, I'm going to screenshot what I just highlighted. And then put it right over here. Oops. And then check for the wording of a question. Okay. Now take a look at this wording of a question. What out of the three, which looks the most like this one? We have a fixed volume proportional to product of a number present and the difference. So you see the word difference, that's the key word here. So I can eliminate exponential growth or exponential growth because this one doesn't have a word difference. What are we taking the difference between upper limit and the number present? Upper limit means limited value, right? So this one over here is this one is the difference between y and the limiting value, and this is both amount to present and the difference between. So I'm looking at logistic. There's a product of present and then difference between the limiting value, so this will be m, and the y. So this is a logistic growth model. So this is how we know the difference between the three. Look for the matching word. Okay, so let's write a sentence here. So this part over here, this is, we will use a logistic growth model. Now, let's add some information here. Suppose initially we have 20 to begin. So I'm going to so let's copy down our function dy dt is equal to, here you can also look at it from here, ky m minus y, and then you have y sub 0 equal to 20, because that's initially means right at the beginning, after 1 hour. So after 1 hour, you have 150. How many after 2 hours. So what we are looking for is y sub 2, the value, how many numbers. Okay, so that's all we have. Now we have the equation given, and then you can use separation of variable and then put all the y term and then t term on the other side and solve. But I told you that this is very challenging. So take a look at this. I have already a solution function solved it. So I'm going to be using this one over here with the condition this. So I'm going to, let's take a screenshot of this one. And then start matching up. So my solution function is already solved, so I do not need to integrate. I'm going to use it right away. Okay, so m, what is m? We have an upper limit, so that's the limit, max limit, so that's m, 375. So that's where I'm going to plug it in m. We also need to find c and then k. So let's do that. C, I have an equation here involves c. I know what y sub 0 is. That's 20. So we can solve for c here. So 20 is equal to m, because y sub 0 is 20, initial value, 1 plus c, cross multiply, m is equal to 20 times 1 plus c. M, we know it's 375. So I have 20 times 1 plus c divided by 20. So 375 divided by 20 is equal to 18.75, 1 plus c. So I'm going to have 17.75 is equal to c. So let's plug it in here. So y is equal to m 375 all over 1 plus c is 17.75 e to the negative kt. Now our equation is y's and k, so we need to solve for k. So we are going to use the second condition given, plug it in. So 1 will be my t input, and then 150 will be my output. So 1 will be my t value. T value. And then 150 will be my y value. So we can solve for k. So 150 is equal to 375. 1 plus 17.75 e raise it to t is 1, so that's a negative k. So let's solve here. Again, cross product. So I have 150. Let me move it over side. Then so 150 let's just times 1 plus 1775 e to the negative k equals 375. Let's divide it by 150. So 1 plus 1775 e raise it to the negative k. That's 375 over 150. I'm going to subtract 1. So 17.75 e to the negative k. Now this part I'm just gonna change to a decimal. Okay, so subtract 1. So 375 over 150 minus 1 will be 1.5 divided by 1775. 1775 e to the negative k is equal to 17.75. 0.08 rounded to the 2 decimal place. Okay. Let me just double check everything looks good. Hmm. 375 divided by 150 minus 1. 1.5 divided by 17.75. And then now let's keep going and then solve for k. So I'm going to copy and paste to the next page. So this is how far we got. So to solve for k, we need to apply ln of ln of e negative k, so ln of 0.08. So this is negative k is equal to ln of 0.08 up. Sorry, I rounded, my mistake. This is 0.08 I'll just carry 4 decimal places because I feel like 2 decimal places is not enough. ln 0.0845. My math lab will tell you how many decimal places. Okay, so watch that. So ln of 0.0845 ended up being negative 2.471 rounded to the 3 decimal place divided by negative 1. K is equal to positive 2.471. So we got k. Now let's go back to our equation here. Remember, this was our original equation. Copy. So replacing k, I'm going to have y is equal to 375 plus 1 plus 17.75 e raised to negative 2.471 t. So this will be our equation, y. So that's good. We solved for y, but our final question is how many after 2 hours. So that's when t equals 2, finding out the y value. So we simply plug it in into our equation. So 375 over 1 plus 17.75 e raised to negative 2.471 times 2. So let's use a calculator to get the answer. So 1 plus, so I'll do that on the side. I am getting, so this is a number of bacteria, so let's round it to the whole number. I get approximately rounded to the whole number 333 paramecia after 2 hours. That's it. So that is our final answer. So this is not too bad. once you have the equation, the general equation, because we just have to substitute and solve for the missing variable. Okay, so let's take a look at the second problem. Now this homework problem, this is an actual homework problem. So let's also read through and see which function, application function this is. Okay. Some homeowner insurance policy includes automatic inflation coverage based on the construction cost index, CCI. Let f of t be the CCI at the time t since January 1st, 1990. Let f of 0 equals 100. Suppose that the construction cost index rising at a rate proportional to, so here's the key word, right? Raising a rate proportional to CCI and index was 127 on January 1st, 1993. Construct and solve differential equation, solve by f of t, determine the CCI will reach 200. So a couple things. I'm just gonna relabel function f as a y because that's just label. So y sub 0 is same thing as like 100 here. So you can write down 100. Okay. And then y sub 3 after 3 year is 127. So those are given. Okay. And then we have y prime. So y prime, what kind of function is this? It's just proportional. There's no word difference. So obviously this is going to be our growth model, exponential growth, because it doesn't have any word difference here. Okay. So this is an exponential growth model. So we will use this one here. So I'm going to screenshot this part. Let's do it one more time. Okay, then use this one to write down solutions. So here, y prime, so this part is just asking to write down, this part is this one because y prime is this one. So my first answer is y prime is equal to ky, which is the exponential growth function. Okay, so you're gonna put that over here. Now we have to find the solution. Fortunately, we do have a solution equation directly right over here. So all we have to do is plug it in and then solve. So let's do that. So I have y is equal to, C is your initial value. So we are given 100. So C is equal to 100 because we are given y sub 0 is 100. So in other words, C is equal to 100. So 100 e raise it to the kt. Now we are going to solve for our k value. So our k value, we need to use this y sub 3 equal to 127 to solve for k. So this is your input t, this is your output y. So let's replace that. 127 is equal to 100 e to the 3k, because I'm replacing t with the 3, divided by 100. I have 1.27 is equal to e to the 3k. To have k, I need to apply ln. So I have ln of 1.27 is equal to 3k divided by 3. Now let's get a decimal number. They want you to round any decimal to the nearest hundredths. That's a 2 decimal place. So I'm getting 0.08 for the k. So what is our equation? Y is equal to C was 100 e to the 0.08k. So that will be right over here. Y is equal to 100 e to the 0.08. I think they want you to use okay, let me see. Oh, they want you to use T, so I'll just use so T, because K is 0.08, so T. Okay? My final answer is the CSI will reach 200 how many years? So how many years? I'm solving for T. So here I have the equation, this part here. Y is equal to 100 e to the 0.08 t. I'm solving for t when y is equal to 200. So let's solve. So 200, 100 e raised to 0.08 t. Now, in order to have t by itself, I'm going to divide it by 100 here. So let's do that. Two is equal to e 0.08 t. Apply ln both sides. So I have ln 2 is equal to 0.08 t divided by 0.08. So t is equal to ln 2 divided by 0.08. I'm getting 8 point, rounded to the nearest tenth, 8.7 years. So that's what I'm gonna put over here, 8.7 years. Okay? So we went and saw logistic growth model. We saw an example of exponential growth. Now let's take a look at our last problem. Okay. This is also your homework problem. Newton's law of cooling states that a rate of change of the temperature of an object is proportional to the difference between the temperature of an object and temperature of surrounding medium. Here's the key word I'm looking at, proportional to the difference between temperature of the object and temperature of the surrounding medium. You see the word difference, so it's going to be either limited growth or logistic growth, correct? But we'll take a look at it in a few minutes. Let's keep reading. Use the law formulate model for the following problem and solve. As a part of manufacturing process, a metal bar is to be heated in an oven until its temperature reaches 600 Fahrenheit. The oven is maintained at a constant temperature 800 Fahrenheit. The temperature of the bar before it's placed on the oven is 100. After 3 minutes of the oven, the temperature of the bar is 400. How long should the bar be left in the oven? Alright, so let's write down a couple things. So first, we have instead of dy dx, it's just variable d capital T and then little t. So t represent the temperature value and then small letter t represent the time. Okay, so there are a couple things given. Temperature of the bar before it's placed. So initially it starts out 100. After 3 minutes, we have a temperature rise to 400. And then we have another one, a constant temperature of 800. And finally, we have, let me see, this one here. We want to know how much the bar should be left. So T when it's reaching the 600. So let's write it out. First one, constant temperature 800. So that's your M, 800. Now before, that's a T sub 0, initially 100 degrees. And then after 3 minutes, you have 400. Your goal is to find a T when capital T is equal to 600. So in other words, what is my T value when it's equal to 600? Okay, and then going back to colors. So I have 600. That's my question that I wanna answer. And then this part is yellow part. This is the pink part. M equal 800 will be my green one here. Okay. So let's go back and then read our question here. So I'm going to screenshot this and then see which one out of the three our model represent. Okay, and I'm also going to delete this one and then put it into a new one. So which one sounds like our model? So we eliminate exponential growth because we have the word difference. Now, what are we taking the difference? Well, difference between, look at the wording, difference between the temperature object and the temperature of surrounding medium. So the difference between two things only. So this will be a limited growth because you're not having a word both between, right? It's literally proportional to and then difference. Proportional to the difference. There's no word inserted as a both present and the difference between. So this will be limited growth model. Okay, so let's put it over here. So this will be a limited growth model. Okay, and let's write our equation for the limited growth model. So dt is equal to k times m minus t. I'm just using this right over here. Instead of y, we have a capital T. Okay, now let's screenshot this here. And see if we can use it. Now here, I want you to take a look at, you have to have every condition meet in order to use the equation. Take a look at this. Here, one of the things that you have to have is the initial value has to be 0. Here, unfortunately, we have initial condition 100. They do not match it. So it's very, very tempting to use this equation, but we cannot use it because C end up here being a zero constant. Here, we are gonna actually have the C value. So even though it's very tempting, you have to check every condition. This does not satisfy, so we actually have to go through. Your equation will look very similar, but there will be C attached. Okay, so we have to do the separation of variable and then do the traditional method. So we cannot do the shortcut. So I just pointed out for you because I want you to know that all these previous two conditions, I was able to use it because I have the initial condition y sub 0 other than 0. I could use it. But in here, this is particularly for equal to 0. I do not have it, so I cannot use it. So let's do the traditional method. So this is going to take a little while because we have to do everything by hand. So let's go through the entire problem doing by hand. So let's replace a couple things that we know of. So I know my m value, so I'm going to replace that. So dt is equal to k times 800 minus t. Now, just like we did it in example 1 and 2, I'm going to separate the variable with a capital T and then small letter t. So let's multiply dt here and then dt here. So the small letter t is on the other side. So I have d capital T is equal to k times 800 minus t dt. I want to have the capital T on the other side. So let's divide it by 800 minus t. So I have 1 over 800 minus t dt equal to k small letter dt. So I have all the capital T on one side and then dt on the other side. K is just a constant, a number, so this is fine. So now we are ready to separate. We already separated. Now we can have an integral on the left-hand side and right-hand side. Here, this part is a u substitution, so let's apply u substitution. U is equal to 800 minus t, so my du dt will be constant disappears, so negative 1, because negative t is negative 1. So we can solve for dt. So I'm going to have du is equal to negative dt. So I divide it by negative 1. So dt is equal to negative 1 du. So I'm going to do that substitution over here. Use substitution. Dt will be this one here. So on the left-hand side, I have 1 over u. Dt will be negative 1 du. I'm going to move the negative 1 on the outside because it's a constant. So negative antiderivative of 1 over u du. I'll do the right-hand side in a minute. I want to finish this one. So over here, let's make it a little bit small. So this will be, that's a ln, so negative ln u plus c, don't forget plus c. Back substitute u, that was 800 minus t, so negative ln 800 minus t plus c. Okay. On the right-hand side, that's easy, that's a constant, so it's a k times the variable t plus c. So on the right-hand side, let me do C1 and C2. KT plus C2. So we need to solve for T. These two I can combine into one. So ln 800 minus T, KT plus big C. Let's copy and then move on to the next page. Okay. Now, oh, oops, I left the negative here, so it should be negative there and negative. So divided by -1, I'm going to have ln 800 minus t minus kt. Now this one is just a constant. It could be positive, it could be negative, depending on what original c is. So I'm just going to put it as a c. The sign does not really matter. Let's apply e functions so that we can have ln disappear. So applying e, so e raised to ln 800 minus t, and then e raised to negative kt plus c. So I have ln of 800 minus t equal to e, oh, actually this disappear. So I have 800 minus t is equal to e raised to the negative kt plus c. So subtract 800, negative t is equal to negative 800 plus e to the negative kt plus c divided by -1, I get t is equal to 800 minus e to the negative kt plus c. All right. So you see that you'll appreciate this one because take a look. If all the condition is met, we could use this equation right away. So we do not have to take all the step to solve for this equation. But you see that if I use this one, I'm missing that plus c. So you need to have that condition met if you want to use it. We were able to use it last time. So let's keep going and solve for c. Okay. So what are some things that we can do to solve for c? I'm going to use the given condition. I'm going to use this one because I like having the zero. So let's use t sub 0 equals 100. So this will be your t and this will be big T. So let's plug it in to solve for c. So 100 is equal to 800 minus e. This will be, if you plug it in 0, so that's just going to be e to the c. Minus 800 minus 800. So that will be negative 700 equal to negative e to the c divided by negative 100. So I have a positive 700 equals e to the c. Apply ln. So c is equal to, because when I apply ln, this cancel out. So c is equal to ln 700. So that's what I'm going to replace it over here. So I have t is equal to 800 minus e to the negative kt plus ln 700. So let's copy this one. We still have to solve for k, and that's where the second condition comes in. This part here, t sub 3 and then equal to 400. So t sub 3 equal to 400. All right, we're almost done. We are halfway through. So we have, let's replace, that's a small letter t. This is capital T. So 400 is equal to 800 minus e to the negative 3k plus ln 700. Subtract 800. So I have negative 400 is equal to negative e minus 3k. Now plus, you know that this plus, I can rewrite that as e to the ln 700. One of the algebra rule when you have x to the a plus b, you can write it as x to the 8, x to the b, product. Because product, you add the exponents. Why did I do that? So I can solve for k more easily. Because e to the ln 700, that's just a number. So let's do that. I'm going to divide this whole thing, because that's just a number, on both sides. So negative e to the ln 700, negative e raised to the ln 700. So all these negative disappear. So 400 is e raised to ln 700. So that will be just 700. E to the negative 3k. So let's apply ln so that we can solve for k. So ln of 400 over 700. And then ln of e to the negative 3k. So ln of 4 over 7, because this reduce, is equal to negative 3k. K is equal to, let's use a calculator, ln 4 over 7 divided by negative 3. I get 0.18654, rounded to the 5 decimal place. Whew. So again, my entire equation, replacing the k onto this one here, my t function is 800 minus e raised to negative 0.18654 t plus ln 700. Now we have an equation. We are almost done. The last part is use this equation to solve for small letter t. So we need to solve t at 600. So that means capital T is 600. So let's do that. So 600 is equal to 800 minus e negative 0.18654 t plus ln 700. So subtract 800, subtract 800. So I'm having negative 200 is equal to negative e. Same trick as earlier. I'm going to separate into two. Negative 0.18654 t. And then e raised to the ln 700. Okay, now same thing here. This part, you can also see that negative, we divided by negative here. Negative 1, negative 1. So I'm going to have, copy. So this will be 200 is equal to e to the negative 0.18654 t. This part here, e's and ln cancel out, which is just times 700. Divided by 700. I have 2 over 7 is equal to e raised to negative 0.18654 t. Let's apply ln both sides. So these cancel out. So ln of 2 over 7 is equal to negative 0.18654 t divided by negative 0.18654 divided by negative 0.18654. So I get t is equal to, our final answer should be negative 0.18654. I'm getting 6.7 minutes. So this part over here, the bar should be left open for 6.7 minutes, nearest 10. Let's finish it up. This part, that's the answer for here. So K times M minus T, 100, 3, 400. All right, that's it. The last problem was a very long problem because we had to manually solve, and then it's not an easy one. So, but it's a really good practice to go through the whole procedure. Okay, on next video, we're gonna begin 9.3.